In this last video of topic 5, we're going to use the deformation property from the previous video to derive Cauchy's integral formula. This relates the value of a complex analytic function at a point to its value around a closed contour that encloses that point. As a recap of what we covered in the previous video, we looked at the deformation property of contour integrals, and we saw that the value of such integrals does not change on deformation of the contour through regions where the integrand is analytic. We also looked at the specific example of the integrand z minus z0 to the power of n, and the integral of that around a closed contour that encloses the point z0 was shown only to be non-zero when n equals minus 1. And the significance of this will be explored further in topic 7 later in the course. The intended learning outcomes for this video are given here. After watching this video, you should be able to derive Cauchy's integral formula and understand what it means. And you should also be able to use Cauchy's integral formula to evaluate contour integrals of the form given by the Cauchy integral formula. This is the last video of topic 5. After watching, I encourage you to attempt the problems in the associated example sheet. There are plenty of problems for you to get practice on all that you've learned throughout this topic. And with that, let's begin this last video of topic 5.
We're going to be looking at Cauchy's integral formula. And this is another very important result in complex analysis. I'm going to spend the rest of the video deriving it, but first of all I'm going to state it. Cauchy's integral formula states, if some complex function f of z is analytic on and within a closed contour C, and we define z0 as a point within that closed contour C, then the following is true. The integral in the normal anti-clockwise sense along the closed contour C of our complex function divided by z minus z0 dz is given by 2 pi I times our complex function evaluated at that point z0. I'll put a red box around this now because it's very important. This is Cauchy's integral formula, and next we're going to derive this. We're going to derive this using the deformation property that we saw in the previous video. We will make use of the deformation property resulting from Cauchy's theorem. Right, let's start proving this. Consider a complex function f of z that is analytic. Remember that means that it's differentiable and single valued in the region of interest, on and within some contour C. Let's draw a picture. We have real and imaginary. And we might have a contour that looks something like this. traversed in the positive anti-clockwise sense by convention. Okay, we're interested in looking at the integral along closed contour C of our function f of z divided by z minus z naught dz, where z naught is any point in the region bounded by C. Bounded by C. Let's put such a point in our picture above. Let's put z naught here. This is the point z naught, internal to the contour C. Okay, next we can note that the integrand in our contour integral here is f of z over z minus z naught. This only fails to be analytic at the point z equals z naught. That is, unless the function value f of z naught disappears there, vanishes there. Okay, so we specified that f of z is analytic on and within the contour C. In the integrand, the only point where the integrand could not be analytic is at the special point z naught, because then the denominator of this function equals 0. However, because the integrand is analytic everywhere else on and within the contour C, we can make use of the deformation property that we derived in the previous video. And we could consider, for example, adding a channel, identifying a subregion where the function is analytic, and going through the same process as last time, where we considered shrinking the channel to have 0 width. However, I'm going to assume the final result that we derived in the previous video, and instead concentrate on choosing some new contour C primed. I'll write this down. Using the result from the previous part, we may deform the contour we've given ourselves above C through the region of analyticity. Of the integrand to another contour. Which contour should we use? Well, let's choose a new contour, C primed, which is a circle centered on z naught and with radius rho. And the radius rho is chosen so that the circle C primed lies within C. And that's for reasons of analyticity. We saw in the last video that such a deformation does not change the value of the integral. Let's draw a picture of our new contour. As before, we have our point z0, and we now have a new circular contour around this point, oriented in the same anti-clockwise sense and of radius rho. Okay, the deformation property has allowed us to rewrite the integral along C of f of z over z minus z0 as the integral along C primed of f of z over z minus z0 dz. How do we approach this integral? Well, let's proceed as we did in the previous video. Let's write z as z0 plus rho e to the I theta for points z that we're interested in for our integral that lie on the contour C primed. This describes a circle. The complex number z has been expressed as the sum of the centre of the circle, z0, and then plus rho e to the I theta. As before, we need the differential dz given by I rho e to the I theta d theta. Performing this substitution, this integral becomes the integral, and then now that we're parameterized in terms of theta, the integration range for the entire circle is going to be from 0 to 2 pi of f of z becomes f of z0 plus rho e to the I theta divided by, we have z minus z0, which is rho e to the I theta, times I rho e to the I theta d theta. Immediately we can see that we can cancel rho e to the I theta from the top and bottom. Taking out a factor of I at the front, this leaves us with I times the integral from 0 to 2 pi of our function f evaluated as z0 plus rho e to the I theta d theta. We're next going to consider what happens if we shrink this radius rho to approach 0. Now, because our function f is analytic and therefore continuous at z0, the value inside the brackets for f of z0 plus rho e to the I theta, that's going to approach f of z0. I'll write that down. We now consider shrinking the radius rho towards 0. As a result, and it's clear from the picture above, f of z in our original integrand is going to approach f of z0, and we can see that from this line here by letting rho approach 0. The integrand is going to approach f of z0. And we're allowed to consider a limit like this because the function f is analytic and therefore continuous. At the point z0. You'll recall that analytic at a point means differentiable at a point, and differentiability implies continuity. That means the line above gives us I times the function evaluated at z0, and then we're left with an integral d theta, and that's a trivial integral which we can perform to leave us with 2 pi I times the function value evaluated at z0. We've therefore shown that the integral from the top line along C of f of z divided by z minus z naught is given by 2 pi I times the function value at z naught. Once again, this is Cauchy's integral formula. This is another remarkable result. On the left-hand side, we have an integral of our function f divided by z minus z naught. That's evaluated along some contour C. And the right-hand side is the value of the function f at some internal point, z naught. What this means is that the value of an analytic function is given at some arbitrary interior point, z naught, once the values of the function along the boundary C are specified. And that this is a remarkable property of complex analytic functions, this non-locality, the fact that you can define the function value within a contour using the values on the contour. I'll write this below. This result means that the value of an analytic function f of z is given at some arbitrary interior point z naught once the values of f, and as a result the values of the integrand, on the boundary C are specified. This is an amazing non-local property of complex analytic functions. In the next topic, we'll see that actually, if the value of the function f is known on the boundary C, then we also get the values of all of the function's derivatives at the point z naught as well. Moreover, if two analytic functions agree, in other words, take the same values on the boundary of a simply connected region, then those two analytic functions agree everywhere within that region as well. To finish this video, I'll write down a very simple example of how to apply Cauchy's integral formula. Imagine we want to determine the integral along a contour C of e to the z over z minus 2 dz. A little picture where we have the real and imaginary axes, and we note that the point of interest here, z naught, lies on the real axis at z equals 2. And let's consider a contour C that encloses this point. It might look something like that. Well, we can immediately apply the result in the red box and note that this is going to be 2 pi I times the function evaluated at the point of interest z naught, where the integrand fails to be analytic. That simply gives us 2 pi I and then times e to the z naught. Z naught is 2, so we get e squared. And we're done. I'll make the final point that if the contour C does not enclose z naught, then the integrand is analytic on and within the contour C. Therefore, Cauchy's theorem holds. And the integral is 0. That's the end of this fourth video of topic 5. As a very quick recap, we used the deformation property that we derived from Cauchy's theorem to show Cauchy's integral formula. This amazing formula allows us to specify the value of an analytic function f at an arbitrary point z0 using the values of that function along an integration contour that encloses z0. And this is an amazing non-local result that we will develop further in the next topic. This marks the end of topic 5, in which we've derived some very exciting properties of contour integrals of analytic complex functions. As usual, you'll get plenty of practice of all that's been covered in the problem sheet. For example, you'll get lots of practice using Cauchy's integral formula, with a particular emphasis on how to use partial fractions to simplify integrals so that you can apply the Cauchy integral formula. Thanks for listening, and next up is topic 6.